thermodynamics of the quantum frustrated Heisenberg model on kagome and triangular lattice. Uh, the theory of frustrated magnetism still offers many challenging questions. With the rapid advance of experimental techniques, many systems can be analyzed on more complex lattice geometries, as the kagome lattice, where the number of the model systems whose classical ground state are massively degenerate in kagome lattice and ferromagnets, giving rise to symmetry breaking effects, fractional magnetization plateaus, hierarchy of energy scales, and the dynamics and amplify role of the second interactions. The nearest neighbors Heisenberg antiferromagnetic model on kagome lattice is described by the Hamiltonian, where I have the matrix given in terms of the phase angle between the two neighbors spins. The spins are assumed form an unordered state. The spin form a coplanar spin structure at 120 degrees. The units used here are the Planck constant is equal to light velocity, Boltzmann constant is equal to 1. In the figure, I have the representation of the system where I have the spin liquid spin for different configuration spins. We consider the cosine of angle phase is equal to minus one half for any pair of spins. The x, z terms do not contribute to the harmonic order in the 1 and the s expansion. We introduce the Holstein-Primakov representation, span the up to first order 1s power is given by this equation. The Hamiltonian is transformed in a harmonic Hamiltonian, where I have three types of bosons. And we obtain after performing the discrete Fourier transform, we find the harmonic spin wave Hamiltonian. I have gamma is a matrix, and I have the vector operator defined by three different boson operator given by this equation. Besides, I have the M matrix. I have the dispersion relief of spin wave energies given by the equation 7. We introduce the XSZ terms to the Heisenberg model given by the equation 8. We obtain the spin wave dispersion relief for the model given by the equation 9 for the dispersive modes and the equation 10 for the flat mode, where I have the definition of gamma key parameters given by this equation. And more or less, I have the vectors delta units of interaction in distance. Instead of x as the correct, an alternative way of generating easy-plane anisotropy is to add a positive single anisotropy term on the model given by the equation 11. In this case, I have the dispersion relief is given by the equation 12. Another important correction to the model is the inclusion of the antisymmetric Jelisinski-Norrie spin coupling given by the equation 13, where I have we consider the vector Jelisinski-Norrie vector is pointed on z direction. And I have the dispersion relief for this case is given by the equation 14, where we define the PM parameter in terms of this Jelisinski-Norrie coupling given by this definition. We obtain the free energy entropy and specific heat for the model using the canonical ensemble, where the free energy is given by in terms of the partition function of the model, and the partition function of the model is obtained for this model Using the dissipation relation for the spin wave obtained by the Hofstadter-Markov, we obtain the entropy given by the equation 15, the specific heat expression given by the equation 16. In the figure, I have the behavior of the entropy of the system as a function of temperature and for different and as a function of different parameters of the system, as the single anisotropy, the Jasinski-Morier, and the anisotropy of the model. We obtain the monotonic increase behavior as a function of temperature for the entropy and the behavior for monotonic decreasing for the entropy as a function of delta D and dm. In figure 3, I obtain the behavior of specific heat of the system as a function of temperature and as a function of anisotropy of the system, Jasinski-Morier interaction, and the single anisotropy. We consider S equal 1/2 in the case in the calculation the system is a spin liquid. Another model that I studied triangular lattice XSD model, and I studied thermodynamic of this model. In this case, the model is given by this Hamiltonian, where I have the external magnetic field in the model. Let's consider is is displayed in the figure where I have this system. I have four different phases of the phase diagram of the model. Uh, we introduce a rotation of the spin operator given by the equation 18, and after that we perform the Hofstadter-Markov transformation expanded until 1s powers for the rotation for the rotated spin operator given by the equation 19. In this case, the Hamiltonian is transformed in the equation 20, where E0 is the energy of the ground state of obtained in the mean field approach. In the figure, I obtain the behavior of the entropy of the system as a function of temperature for different values of anisotropy gamma and for different modes of, of magnons and for a specific value of external magnetic field given by 1.1, where the system presents a phase transition. In the figure 6, I obtain the behavior of the specific heat of the model. In this case, I have the specific heat that present a large peak, and the specific heat suffers a large variation of the anisotropy of the system. I have the sudden decreasing or the sudden falling of the specific heat at low temperature limit, indicating a discontinuity of the specific heat, indicating a fast-order phase transition on the model. In the figure 7, I obtain the behavior of magnetization of the system for different values of anisotropy lambda in different modes of magnons. We obtain the point where the the extinction of magnetization for as a temperature indicates a change, a loss of magnetization of the system, and consequently, a phase transition for the paramagnetic state. In the figure 8, I obtain the magnetic susceptibility behavior for the system as a function of temperature for different values of anisotropy lambda and for a a fixed value of external field H 1.1. I obtain strong variation with the anisotropy of the system lambda for different modes of magnons. I studied the topology of magnon bands and spin Hall conductivity of this for the triangular lattice of the Heisenberg mode. The topological properties of the system, the Barry is described by the Barry phase given by the equation 21 and the Char number of the bands given by the equation 22. I obtain the spin-Hall conductivity given by this equation 23 and the thermo-Hall conductivity by the equation 24, given by in terms of the Barry curvature of the N-band of magma. C2x is given by in terms of the G logarithm function given by this expression. I write the states given by this equation and obtain the expression for the Barry curvature given by the equation 25. Making an analytical calculation, obtain the following expression for the Barry curvature for the different magnum bands of the system, 1 and 3. In the figure 9, I obtain the behavior of the spin-Hall conductivity as a function of temperature for different values of lambda, the anisotropy of the system, for a value of external magnetic field held fixed and Jarosinski-Maury constant held fixed too. I have at zero temperature, the spin-Hall conductivity tends to zero due to the absence of magnetic station at zero temperature. In convey, as the temperature increases, magnets are thermally excited, and I have the spin-Hall conductivity finity. The behavior of the spin-Hall conductivity in a triangular lattice and ferromagnetic is up to studying using analytical and numeric techniques. I have the linear spin wave theory is commonly employed to investigate this system. However, at low temperature, the low bands dominate. Increase the temperature, the two bands have almost the same contribution, and the spin-Hall conductivity decrease. However, we must note the difference between the behavior of boson and Fermi, while the former Fermi distributes one at T zero temperature, the Hall conductivity for Fermi is proportional to the sum of Char number of the free band, hence the Hall conductivity is finite even at zero temperature. We have the Hall conductivity zero at zero temperature limit. As a conclusion, we analyze the thermodynamic quantity in the quantum frustrated two-dimensional antiferromagnet on kagome lattice using the linear spin wave theory and analyze the thermodynamic property in the Heisenberg model on triangular lattice with three sublattices denoted by A, B, and C. The splitting of magnets in the antiferromagnetic acts as the model on triangular lattice in the presence of external magnetic field can have a significant impact of the physical properties of the system, leading to complex and interesting behavior. Thank you very much for your attention.